Hello, and welcome back to another journey through the cosmos. Before we begin today's exploration, I'd like to ask for your support. If you enjoy this content, please consider subscribing to the channel. Your subscription helps us continue creating these peaceful explorations of science and space. A simple like on this video also makes a meaningful difference, helping others discover this calming corner of knowledge. And if you're finding this relaxing, the algorithm appreciates when you watch a little longer. So settle in, get comfortable, and let's explore together what the James Webb Space Telescope has revealed to us. Today, we're going to talk about something extraordinary: the James Webb Space Telescope, humanity's most advanced eye on the universe, has been sending back images and data that have transformed our understanding of everything beyond our world. But there's something interesting about how this information reaches us. Not everything the telescope observes is immediately shared. Not everything it discovers is quickly explained. Some findings take years to understand. Some images require extensive analysis before they can be released. And some discoveries are so complex, so challenging to our current models, that scientists proceed with careful deliberation before speaking publicly. This isn't conspiracy. This is science working as it should: careful, methodical, thoughtful. So let's explore, calmly and thoroughly, what James Webb has shown us, what it continues to reveal, and why some discoveries take time to reach the world. The telescope that looks through time. The James Webb Space Telescope floats in space far from Earth, positioned at a point called L2, the second Lagrange point. This location is approximately 1 million miles from our planet, in the direction opposite the Sun. At this distance, the telescope maintains a stable position relative to Earth, requiring minimal fuel to stay in place. It's a quiet spot in space, far from the interference of Earth's heat and light, far from the disruptions of our atmosphere. Webb is not like the telescopes you might imagine. It doesn't look like the instruments in observatories on mountaintops.
It doesn't resemble the small telescopes people use in their backyards to observe the moon and planets. Webb is something different entirely. Its primary mirror measures 21 feet across, composed of 18 hexagonal segments made of beryllium, coated with a microscopically thin layer of gold. Gold reflects infrared light particularly well, and infrared light is what Webb was designed to detect. Why infrared? Because the universe is expanding. As it expands, light from distant objects stretches along with space itself. This stretching shifts visible light toward the red end of the spectrum and beyond, into infrared wavelengths invisible to human eyes. The most distant objects in the universe, the oldest galaxies, the first stars that formed after the Big Bang, all send their light to us in infrared. To see the earliest universe, to witness cosmic dawn, we need to observe in infrared, and that's precisely what Webb does. The telescope is cold, extremely cold. Most of its instruments operate at temperatures just a few degrees above absolute zero, colder than the coldest natural places in the universe. This cold is necessary. Infrared light is essentially heat radiation. If the telescope itself were warm, its own heat would overwhelm the faint infrared signals from distant galaxies. So Webb hides behind a sun shield the size of a tennis court, made of 5 layers of material thinner than a human hair, each layer separated by space to maximize insulation. This shield keeps the telescope's instruments at approximately -370 degrees Fahrenheit, while the sun-facing side of the shield heats to around 230 degrees Fahrenheit. The temperature difference is extraordinary, yet the system works perfectly, maintaining the frigid conditions necessary for observation. Building Webb took decades. The project began in the late 1990s, though the concept emerged even earlier. Engineers and scientists from 14 countries contributed to its design and construction. Thousands of people worked on various components, solving problems that had never been solved before. The mirror segments, for instance, needed to be lightweight yet perfectly shaped, capable of withstanding the violence of launch while maintaining their precise geometry.
Each segment can be adjusted independently, moved by tiny motors to align with the others, creating a single perfect mirror surface despite being composed of separate pieces. The telescope launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. The launch was perfect. Every stage worked flawlessly, but the journey had only begun. Webb was folded for launch, compressed into a space much smaller than its full size, like an intricate origami sculpture. Over the following month, as it traveled toward L2, it slowly unfolded. The sun shield deployed, layer by layer. The mirror segments extended into position. Secondary mirrors moved into place. Every deployment was irreversible. If something went wrong, there would be no repair mission. Unlike the Hubble Space Telescope, which orbits close to Earth and was serviced multiple times by astronauts, Webb is far beyond human reach. Everything had to work perfectly the first time. And it did. By mid-January 2022, Webb reached its destination. Engineers began the careful process of aligning the mirror segments, adjusting each one until all 18 worked together as a single mirror. This alignment took months. Light from a single star was used as a reference point. Engineers adjusted each segment until that star appeared not as 18 separate images, but as one perfect point of light. The precision required was extraordinary. Each segment needed to be positioned with accuracy measured in nanometers, distances smaller than a wavelength of light. Slowly, patiently, the telescope came into focus. Then came calibration. Each instrument aboard Webb needed to be tested, characterized, understood completely. Scientists took images of known objects, comparing Webb's observations with data from other telescopes. They learned how their new instruments saw the universe, how its detectors responded to different wavelengths, how to convert raw data into meaningful images. This process also took months. There was no rushing. Every step required careful attention, methodical verification. Finally, in July 2022, the first images were released to the public. Those images astonished the world. They showed galaxies in unprecedented detail, stars being born inside clouds of gas and dust, exoplanet atmospheres, dying stars ejecting their outer layers into space. The universe appeared in ways we had never seen before. Colors represented different wavelengths of infrared light, translated into visible colors so human eyes could appreciate them. Structures invisible to previous telescopes emerged in sharp clarity. And these were just the first images, the beginning of what Webb would reveal. Since then, the telescope has continued observing, night after night, gathering light from the distant universe. It doesn't observe continuously. Like any telescope, it schedules its time carefully. Astronomers from around the world submit proposals, requesting time to observe specific targets. A committee reviews these proposals, selecting the most scientifically valuable observations. Some observations take hours, some take days. Some targets are observed multiple times, building up enough light to see extremely faint details. The data comes down to Earth through the Deep Space Network, a collection of large radio antennas located around the world. Webb sends its observations in radio signals, transmitting terabytes of data. This data goes to the Space Telescope Science Institute in Baltimore, Maryland, where it's processed, calibrated, and distributed to the astronomers who requested it. Those astronomers then begin their own analysis, looking for discoveries, testing hypotheses, seeking to understand what they're seeing. This is where the delay occurs. This is why some discoveries take time to reach the public. Scientific analysis is not instantaneous. When Webb observes a distant galaxy, the raw data is just numbers, measurements of light intensity at different wavelengths in different parts of the image. Scientists must convert these numbers into meaningful information. They must compare the new observations with theoretical models. They must check their results, verify their interpretations, consider alternative explanations.
They must write papers describing their findings, submit those papers to scientific journals, and respond to peer review, where other scientists examine the work, ask questions, suggest improvements, verify that the conclusions are justified by the data. This process takes time, usually months, sometimes years, and only after a discovery has been thoroughly analyzed, peer-reviewed, and published does it typically reach the general public through press releases and news articles. This is not secrecy. This is the normal, healthy pace of careful science. It's the difference between saying something quickly and saying something correctly. But even understanding this process doesn't fully explain what people mean when they wonder about what Webb has kept hidden. There's something more interesting happening, something worth exploring carefully and calmly. Webb observes things that challenge our understanding. It sees galaxies that shouldn't exist according to our previous models. It detects chemical signatures in exoplanet atmospheres that we didn't expect. It reveals structures in the early universe that seem too mature, too organized for their age. These aren't secrets being kept from the public. They're mysteries that scientists themselves are still trying to understand. And speaking about them prematurely, before the analysis is complete, would create more confusion than clarity. Let me give you an example. In its first year of operation, Webb observed galaxies from when the universe was only a few 100 million years old. According to our previous understanding, galaxies this early should be small, irregular, still forming. Instead, Webb saw some galaxies that appeared large, well-organized, with structures suggesting they had been evolving for longer than should have been possible. This was surprising, very surprising. Some scientists wondered if our understanding of galaxy formation was incomplete. Others suggested that the galaxies might look different than they actually were, that we might be misinterpreting the data somehow. Papers were written, debates occurred at conferences, more observations were scheduled to gather additional data. Slowly, understanding emerged.
Some of those early galaxies were indeed unusual, pushing the boundaries of our models, suggesting that galaxy formation in the early universe happened faster or differently than we thought. But some of the initial interpretations were too extreme. As analysis continued, more nuanced pictures emerged. The universe was revealed to be more complex than our simplest models suggested, but not incomprehensibly so. Our theories needed adjustment, not abandonment. This is how science works. First comes observation, then comes interpretation, then comes debate, further observation, refined interpretation, gradually converging on understanding. The public often sees only the first step and the last step, observation and understanding, without witnessing the long middle process of figuring out what the observations mean. This can create the impression that information is being hidden, when actually it's being carefully processed. Webb has also observed things that scientists are still analyzing, findings that haven't yet been published because the work isn't complete. Right now, at this moment, there are images sitting in computer databases that show details no human has fully understood yet. There are spectra, graphs showing the intensity of light at different wavelengths, that contain information about the composition of distant atmospheres or the chemistry of ancient stars, information that researchers are still extracting, still comparing with models, still verifying. These aren't secrets, they're works in progress. And there's another category of observation worth understanding. Webb sometimes sees things that are genuinely unexpected, things that don't fit any model, things that seem to contradict what we think we know. When this happens, scientists proceed with exceptional caution. They check for instrumental errors, cosmic rays hitting the detector, processing mistakes, calibration issues, anything that might create a false signal. They look at the same target again if possible, trying to verify that what they saw was real. They consult with colleagues, sharing data, asking for independent analysis.
Only after extensive checking, after ruling out all the mundane explanations, do they begin to consider that they might have observed something genuinely new, something that requires rethinking our understanding. This caution is not covering up discoveries, it's protecting against false discoveries, against announcing something dramatic that later turns out to be a mistake. The history of astronomy includes several embarrassing episodes where scientists announced major discoveries that subsequent analysis proved wrong. Everyone remembers the excitement and disappointment of the supposed detection of phosphine in Venus's atmosphere, initially interpreted as potential evidence of life, later revealed to be a more mundane chemical signal misidentified in complex data. Scientists learned from such experiences. They learned to be more careful, to verify more thoroughly before making public announcements. So when people wonder about what Webb has kept hidden, they're usually wondering about three things: discoveries still being analyzed, observations that challenged our models and required time to understand, and the general scientific process of verification that occurs between observation and announcement. None of these represent actual secrecy. All represent science working properly, carefully, methodically. But let's go deeper. Let's explore what Webb has actually shown us, starting with the most distant objects it has observed, the oldest light in the universe, images of cosmic dawn. The universe is approximately 13.8 billion years old. We know this from multiple lines of evidence: measurements of the cosmic microwave background, observations of the oldest stars, calculations based on the expansion rate of space. The very first stars, the first galaxies, formed when the universe was only a few 100 million years old. Before that, space was filled with neutral hydrogen gas, dark and quiet, slowly collapsing under gravity into the first structures. Webb was specifically designed to observe this era, called the epoch of reionization.
This period, roughly from 100 million to 1 billion years after the Big Bang, saw the first stars ignite, their ultraviolet light gradually ionizing the hydrogen around them, making space transparent to light. Before reionization, the universe was opaque, filled with neutral gas that absorbed most light. After reionization, space became clear, allowing light to travel freely across cosmic distances. Understanding this transition, observing the objects that caused it, represents one of astronomy's major goals. And Webb is delivering. It has now observed dozens of galaxies from this early era, some from when the universe was only 300 million years old. These galaxies appear as tiny red dots in Webb's images, their light stretched by cosmic expansion into deep red and infrared wavelengths. Without Webb's infrared vision, they would be invisible. Even to Webb, they're faint, requiring hours of exposure time to gather enough light to analyze. But that analysis reveals extraordinary things. By spreading the light into a spectrum, separating different wavelengths, scientists can identify the chemical elements present in these ancient galaxies. They can measure how fast the galaxies are moving, whether they're rotating, whether they're colliding with other galaxies. They can estimate how many stars they contain, how rapidly they're forming new stars, what their stars' temperatures and ages are. What they're finding is fascinating. These early galaxies were busy places, forming stars at prodigious rates, sometimes creating the equivalent of hundreds of suns worth of new stars every year. For comparison, our Milky Way currently forms only about 1 or 2 new stars annually. These ancient galaxies were in a hurry, converting their gas into stars rapidly, building up mass quickly. Some of these galaxies also appear more organized than expected. They show rotating disks, spiral structures, central bulges, features that suggest orderly evolution over time. But they're so young. How did they organize so quickly? This is one of the puzzles Webb has presented. Current models of galaxy formation suggest that early galaxies should be messy, irregular, chaotic, slowly settling into organized structures over billions of years.
Yet here are galaxies only a few 100 million years old, showing surprising maturity. Several explanations are being explored. Perhaps stars formed even earlier than we thought, giving these galaxies more time to evolve. Perhaps dark matter, the invisible substance that provides the gravitational framework for galaxy formation, is distributed differently than our models assume, allowing faster assembly. Perhaps the first generation of stars, made purely of hydrogen and helium without any heavier elements, had different properties than modern stars, affecting how quickly galaxies could form. Or perhaps we're misinterpreting what we're seeing, mistaking appearance for reality in some subtle way. The answer isn't clear yet. Research continues. More observations are being made. More detailed models are being developed. Eventually,
understanding will emerge, but it takes time. This is one of those cases where Webb has shown us something unexpected, something that requires rethinking our models, something that scientists are actively working to understand. Webb has also revealed the most distant individual stars ever observed. Normally, stars are too faint to see across cosmic distances. Even our most powerful telescopes can't detect individual stars in distant galaxies. We see only the combined light of billions of stars blended together. But occasionally, a phenomenon called gravitational lensing allows us to see farther. Gravitational lensing occurs when a massive object, like a galaxy cluster, sits between us and a more distant object. The cluster's gravity bends space, acting like a cosmic magnifying glass, amplifying and brightening the light from objects behind it. Sometimes this lensing can magnify an individual star enough to make it visible across billions of light years. Webb has now observed such magnified stars from when the universe was less than 1 billion years old. These are individual stars, single points of light, visible despite being extraordinarily distant. By analyzing their light, scientists can learn about the properties of the very first generation of stars, stars made purely from the primordial elements created in the Big Bang, without any of the heavier elements that would later be produced in stellar cores and spread through space by supernova explosions. These first-generation stars, called population 3 stars, have never been directly observed before. They should have been massive, extremely hot, burning through their fuel quickly and exploding as supernovae after only a few million years. They should have produced the first heavy elements, carbon, oxygen, iron, all the elements necessary for planets and life, elements that didn't exist when the universe was young. Finding and studying these stars has been a goal of astronomy for decades. Webb might have found them. Some of the magnified stars it has observed show unusual properties, spectra that could indicate very low levels of heavy elements, possibly consistent with first-generation stars. But the analysis is complex. The magnification from gravitational lensing can distort the light in subtle ways. The stars might not be what they appear. Scientists are working carefully to understand what they're seeing, comparing observations with models, trying to verify whether they've truly detected population 3 stars or whether they're observing something else. This is another example of a discovery that takes time to confirm. The observations exist, the data is real, but interpreting that data, understanding what it means, requires careful work. And until that work is complete, until scientists are confident in their interpretation, they're appropriately cautious about making definitive announcements. Webb has also observed the most distant black hole ever detected, a supermassive black hole billions of times the mass of the Sun, existing when the universe was only about 500 million years old. This is surprising because supermassive black holes should take time to grow. They start as smaller black holes formed from the collapse of massive stars, then grow by consuming surrounding gas and stars, gradually building up mass over millions or billions of years. But this black hole is already supermassive while the universe is still young.
How did it grow so large so quickly? Did it start from a more massive seed than expected? Did it consume matter at weights higher than we thought possible? Did it form through some alternative mechanism, perhaps directly from the collapse of a massive cloud of gas, without going through a stellar stage first? These questions are being actively researched. The discovery is real. The puzzle is genuine. The answers are still emerging. Another fascinating discovery involves the detection of complex organic molecules in the atmospheres of exoplanets, planets orbiting stars other than the Sun. Webb's instruments can observe starlight passing through an exoplanet's atmosphere during transit, when the planet passes in front of its star from our perspective. As the starlight filters through the atmosphere, certain wavelengths are absorbed by molecules in the atmosphere, creating a unique spectral signature that reveals which molecules are present. Webb has detected water vapor, carbon dioxide, methane, and more complex molecules in several exoplanet atmospheres. This is extraordinary. We're analyzing the air of worlds dozens or hundreds of light years away,
determining their composition, learning about their chemistry. Some of these molecules are associated with biological processes on Earth. Does their detection elsewhere suggest life? Not necessarily. All of these molecules can be produced by non-biological processes as well. But their presence tells us about the conditions on these worlds, about their temperatures, their atmospheric dynamics, their potential habitability. One particularly interesting target is a planet designated K2-18b, orbiting a red dwarf star about 120 light-years away. This planet is larger than Earth but smaller than Neptune, in a category called sub-Neptunes, a type that doesn't exist in our solar system. It orbits in its star's habitable zone, the range of distances where temperatures might allow liquid water to exist. Webb's observations detected water vapor and carbon dioxide in its atmosphere, along with possible traces of dimethyl sulfide, a molecule that on Earth is primarily produced by biological activity, specifically by ocean phytoplankton. Does this mean K2-18b has life? Almost certainly not.
The detection of dimethyl sulfide is tentative, requiring further verification. And even if confirmed, there are non-biological ways to produce this molecule, especially in an environment very different from Earth. K2-18b likely has a thick hydrogen atmosphere, possibly with a water ocean beneath, possibly with a rocky core deep below, a configuration unlike anything in our solar system. We don't fully understand such worlds yet. We're only beginning to study them. But the observation is tantalizing. It shows that Webb can detect complex organic molecules in exoplanet atmospheres. It demonstrates that we now have the capability to search for potential biosignatures, chemical signs that might indicate biological activity. And it reminds us how much we still don't know, how many mysteries remain. This is another discovery that requires time to understand fully. The data is being analyzed carefully. Alternative explanations are being explored. Additional observations of K2-18b and similar planets are being planned. Eventually, we'll have a clearer picture. But for now, we have an intriguing hint, a possibility, a direction for future research. Webb has also revealed new details about the death of stars. When stars like the Sun exhaust their fuel, they expand into red giants, shedding their outer layers into space in beautiful structures called planetary nebulae. Webb's infrared vision penetrates the dust in these nebulae, revealing details invisible to optical telescopes. The images are stunning, showing intricate shells, jets, bubbles, structures shaped by magnetic fields, stellar winds, and the orbits of unseen companion stars. These nebulae return material to space, enriching the interstellar medium with heavy elements created in the star's core. This enriched material will eventually form new stars, new planets, continuing the cycle of cosmic recycling. We are made of material from ancient stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created inside stars that died billions of years ago, releasing their contents to space, providing the raw materials for the solar system and Earth and life. Webb allows us to observe this process in unprecedented detail. We can see which elements are being released, where they're going, how they mix with surrounding gas. We can watch stellar death enriching the cosmos, preparing for the next generation of stars and worlds. The telescope has also observed star birth, looking deep into molecular clouds, dense regions of gas and dust where new stars form. These clouds are opaque to visible light, hiding their contents, but infrared light penetrates dust, allowing Webb to see inside, revealing protostars, young stars still gathering mass from surrounding material, still growing, still evolving toward the stable hydrogen-burning phase that will sustain them for billions of years. The images show stars in various stages of formation, some just beginning to collapse from diffuse gas, some surrounded by disks of material from which planets will form, some already igniting nuclear fusion in their cores, beginning their long lives as stable stars. These observations help us understand how stars form, how planetary systems develop,
how the process that created our own sun and solar system 4.5 billion years ago continues throughout the universe. One particularly beautiful target is the Carina Nebula, a vast star-forming region about 7,500 light-years from Earth. Webb's image of the Carina Nebula shows towering cliffs of gas and dust, sculpted by radiation and stellar winds from young massive stars. Hidden within these cliffs are dozens of newly forming stars, visible in infrared but invisible in optical light. The image resembles a cosmic landscape, mountains and valleys carved by starlight, glowing in infrared, revealing a nursery where new suns are being born. Another target is the Pillars of Creation, a famous structure in the Eagle Nebula imaged previously by the Hubble Space Telescope. Webb's infrared view reveals far more stars than Hubble could see, showing the full population of young stars embedded in the pillars, still shrouded in their natal cocoons of gas and dust. The comparison between Hubble's visible light image and Webb's infrared image is striking, showing how different wavelengths reveal different aspects of the same cosmic objects. Webb has also studied our own solar system in surprising detail.
It has observed the outer planets, Jupiter, Saturn, Uranus, Neptune, revealing atmospheric features, storms, auroras. It has watched moons of these planets, looking for geysers, analyzing surface compositions, searching for signs of subsurface oceans. It has observed asteroids and comets, studying their compositions, learning about the primitive materials from which the solar system formed. One fascinating observation involved Jupiter's moon Europa, thought to harbor a global ocean beneath its icy crust. Webb searched for plumes of water vapor erupting from the surface, geysers that might be spraying ocean water into space, offering a chance to sample the ocean's composition without drilling through miles of ice. The observations were inconclusive, neither clearly detecting plumes nor ruling them out. More observations are planned. This is another example of work in progress, science proceeding carefully, gathering data, building understanding over time. Webb has even turned its gaze toward Mars, observing our planetary neighbor in infrared, mapping surface temperatures, tracking dust storms, studying atmospheric circulation. Mars appears different in infrared than in visible light, showing temperature variations that reveal details about surface composition and atmospheric dynamics. All of these observations, from the most distant galaxies to our neighboring planets, contribute to a comprehensive picture of the universe, from its earliest moments to the present day, from the largest scales to the details of individual worlds. Webb is not just one discovery, it's thousands of observations, each adding to our understanding, each revealing some aspect of cosmic reality. But understanding what Webb has shown us requires more than just looking at images. It requires understanding what we're seeing, what different colors and brightnesses mean, what the presence or absence of certain features tells us. It requires context, knowledge of what previous telescopes had shown, awareness of what questions scientists were trying to answer. And it requires patience. The universe is complex. The answers to our questions are not always simple. Sometimes the data raises more questions than it answers. Sometimes what appears clear at first becomes mysterious upon closer examination. Sometimes mysteries persist for years before solutions emerge. This is the nature of exploring the unknown. We don't always find what we expect. We don't always understand immediately what we're seeing. Sometimes we must sit with uncertainty, with incomplete information, with competing hypotheses, waiting for additional data, better models, deeper analysis. But this uncertainty is not frustration, it's opportunity. It's the frontier of knowledge, the place where new understanding is forged. Every mystery Webb reveals is an invitation to think more carefully, to develop better theories, to design new observations, to push the boundaries of what we know. So what has Webb kept hidden? Nothing, truly. Everything it observes eventually becomes public. All data enters archives accessible to researchers worldwide. All discoveries, once verified and understood, are published in scientific journals and announced to the world.
What creates the impression of hidden information is simply the time required for science to work properly, the gap between observation and understanding, the period of analysis, verification, debate, refinement that transforms raw data into reliable knowledge. This gap is not a bug, it's a feature. It's what prevents false discoveries from being announced as fact. It's what ensures that when scientists do make announcements, those announcements are based on solid evidence, careful analysis, thorough checking. And during this gap, while analysis proceeds, while scientists work to understand what they're seeing, the rest of us can appreciate the wonder of the process itself. We can marvel at humanity's ability to build an instrument capable of seeing across billions of light years, to gather light that has traveled for most of the universe's history, to extract information from that ancient light, to learn about the cosmos. We can reflect on how far we've come. A century ago, we didn't know galaxies existed beyond our own. We thought the universe was static and eternal. We had no idea of the Big Bang, of cosmic expansion, of the universe's history and evolution.
Now we observe that history directly, seeing galaxies as they were billions of years ago, watching the universe's story unfold. And we can look forward to what Webb will show us in the years ahead. The telescope is designed to operate for at least 10 years, possibly 20 or more. It has only been observing for a little over 2 years. Most of its work still lies ahead. Most of its discoveries haven't been made yet. What will it find? We don't know. That's the beautiful part. That's why we explore. Not to confirm what we already believe, but to discover what we don't yet know. Not to see what we expect, but to be surprised, to be challenged, to have our understanding deepened and enriched. Webb is showing us the universe as it truly is, in all its complexity, mystery, and beauty. And as we continue to analyze its observations, to understand its discoveries, to grapple with the questions it raises, we're participating in one of humanity's grandest endeavors, the attempt to understand the cosmos, to know our place within it, to appreciate the extraordinary reality of existence. This is not hidden. This is shared. This is science as it should be, careful, thorough, honest, and ultimately, wonderfully illuminating. The architecture of cosmic time. Now that we've explored what the James Webb Space Telescope is and how it operates, let's journey deeper into what it has revealed about the structure of the universe itself. Let's talk about time, about distance, about the fundamental architecture of reality as Webb allows us to see it. When we look at the night sky, we're not seeing the present, we're seeing the past. Light travels at a finite speed, approximately 186,000 miles per second. This seems impossibly fast by human standards, yet cosmic distances are so vast that even at this speed, light takes time to cross them. The light from the moon takes about 1¼ seconds to reach Earth. Sunlight takes 8 minutes. Light from the nearest star beyond the Sun, Proxima Centauri, takes 4.2 years. We see that star not as it is now, but as it was 4.2 years ago. This might seem like a limitation, but it's actually an extraordinary gift. It means telescopes are time machines. When Webb observes a galaxy 10 billion light-years away, it sees that galaxy as it was 10 billion years ago. The light has been traveling through space for 10 billion years, carrying information about what that galaxy looked like, what it was doing, what it contained, all those eons ago. By the time the light reaches us, that galaxy has evolved, changed, possibly merged with other galaxies, possibly died entirely. But we see its past, preserved in light. This transforms astronomy into a historical science. We don't just study the universe as it is now.
We study its entire history, seeing different eras by looking at different distances. Nearby objects show us the recent past. Distant objects show us the deep past. The most distant objects show us the universe in its infancy. Webb excels at this historical observation. By looking at galaxies at different distances, it maps cosmic history, seeing how galaxies have evolved over billions of years, how star formation rates have changed, how the chemical composition of the universe has been enriched over time. It's like having photographs of the same person at different ages, from infancy through childhood, adolescence, adulthood, old age, allowing us to understand how that person developed over a lifetime. Webb gives us similar photographs of the universe at different cosmic ages. The universe itself is approximately 13.8 billion years old. We know this with surprising precision, derived from multiple independent measurements that all agree remarkably well. The cosmic microwave background, the afterglow of the Big Bang, encodes information about the universe's age in its temperature fluctuations. The oldest stars in globular clusters set lower limits on cosmic age, since the universe must be at least as old as its oldest stars. The expansion rate of space, measured by observing how fast distant galaxies are receding from us, allows us to calculate backward to determine when everything was compressed to a point. All these methods converge on the same answer: 13.8 billion years, give or take a few hundred million years. This is the timeline Webb explores. This is the history it reveals.
At the beginning, immediately after the Big Bang, the universe was extraordinarily hot and dense, a plasma of elementary particles, quarks and electrons and photons, too energetic for atoms to exist. As space expanded, it cooled. Within minutes, protons and neutrons combined to form the first atomic nuclei, primarily hydrogen and helium. After about 380,000 years, the universe had cooled enough for electrons to combine with these nuclei, forming the first complete atoms. This moment, called recombination, made the universe transparent. Before recombination, photons scattered constantly off free electrons, unable to travel far. After recombination, with electrons bound into atoms, photons could travel freely. The light released at that moment is what we now observe as the cosmic microwave background, stretched by cosmic expansion from visible light into microwave wavelengths. After recombination came the cosmic dark ages, a period when the universe was filled with neutral hydrogen gas, dark and quiet, without stars or galaxies. Gravity worked slowly during this time, pulling gas into denser regions, creating the first structures. Current models suggest the first stars ignited about 100 million years after the Big Bang, perhaps earlier, perhaps later. We're not certain because we haven't observed them yet. Even Webb can't see individual stars from that era, though it's trying. These first stars were different from modern stars. They formed from primordial gas containing only hydrogen and helium, without any heavier elements. This affected their properties. They were likely very massive, hundreds of times the mass of the Sun, burning extraordinarily hot and bright, producing intense ultraviolet radiation that began ionizing the hydrogen around them. They lived fast and died young, exploding as supernovae after only a few million years, ejecting the first heavy elements into space, seeding the universe with carbon, oxygen, silicon, iron, all the elements created in their cores through nuclear fusion. These explosions also left behind remnants, neutron stars and black holes, dense objects that would become the seeds for larger structures.
Some of these black holes began consuming surrounding gas, growing, eventually becoming the supermassive black holes found at the centers of galaxies. How this growth occurred, how stellar mass black holes became billion solar mass monsters, remains one of astronomy's open questions. The first galaxies assembled from collections of these early stars and the gas clouds surrounding them. They were small by modern standards, irregular, chaotic, but they represented the beginning of cosmic structure. Over time, these small galaxies merged, combining to form larger galaxies, a process that continues today. Galaxy formation is hierarchical, building from small to large, from simple to complex. Webb observes this process across cosmic time.
It sees small galaxies in the early universe, billions of years ago. It sees larger galaxies at intermediate distances, representing intermediate cosmic times. It sees mature galaxies nearby, representing the recent past. By comparing galaxies at different epochs, astronomers can track how galaxies grow, how they change, how they evolve from the simple structures of the early universe to the complex spirals and ellipticals we see around us today. One of the surprising findings from Webb's first years involves how quickly some early galaxies became organized. As mentioned earlier, some galaxies observed from when the universe was only a few 100 million years ago show rotating disks, spiral arms, central bulges, structures suggesting orderly evolution. This was unexpected. Previous models suggested early galaxies should be irregular and chaotic, taking billions of years to develop organized structures. Why the discrepancy? Several possibilities are being explored. Perhaps our models underestimate how quickly gas can settle into rotating disks. Perhaps dark matter, which provides the gravitational scaffolding for galaxy formation, is distributed differently than we assumed, allowing faster assembly. Perhaps we're misinterpreting what we're seeing, mistaking temporary configurations for stable structures, or seeing galaxies from unusual angles that make them appear more organized than they actually are. Research continues. More observations are being made. More sophisticated models are being developed.
The answer will emerge, but it requires patience, careful work, thorough analysis. This is one of those cases where Webb has challenged our understanding, forcing us to reconsider our assumptions, refine our theories. Another fascinating aspect of cosmic history involves the changing rate of star formation over time. In the early universe, galaxies formed stars rapidly, converting their gas into stars at prodigious rates. Star formation peaked when the universe was about 3 billion years old, during what astronomers call cosmic noon. At that time, galaxies throughout the universe were forming stars at rates 10 to 100 times higher than today. The universe was ablaze with stellar birth, creating the majority of stars that exist today. Since cosmic noon, star formation has declined. Galaxies have gradually exhausted their supplies of cold gas, the raw material for star formation. Some gas has been heated by supernova explosions and black hole activity, becoming too hot to collapse into stars. Some gas has been expelled from galaxies entirely, blown out by powerful galactic winds. The universe has gradually shifted from a phase of rapid star formation to a more quiescent state, where most galaxies form stars slowly, if at all. Webb can observe this transition directly by looking at galaxies at different distances. Distant galaxies, seen as they were billions of years ago, show high star formation rates. Intermediate distance galaxies show moderate rates. Nearby galaxies show low rates. The decline is clear, measurable, consistent across different types of galaxies. This decline has implications for the future. Star formation will continue to decline. Billions of years from now, star formation will essentially cease. The universe will gradually dim as existing stars exhaust their fuel and die, without new stars being born to replace them. Eventually, in the far future, perhaps 100 trillion years from now, the last stars will flicker out, leaving the universe dark and cold, filled with dead stellar remnants, black holes, and dispersed gas too dilute to form new stars. But that future is unimaginably distant. For now, star formation continues, albeit at a slower pace than in the past.
And Webb allows us to observe the full history of this process, from the burst of star formation in the early universe through cosmic noon to the present gradual decline. The telescope has also revealed details about the cosmic web, the large-scale structure of the universe. On the largest scales, matter is not distributed uniformly. Instead, it forms a web-like pattern of filaments, sheets, and voids. Galaxies cluster along the filaments, which are regions of higher density. Between the filaments lie voids, vast empty regions containing few galaxies. This structure emerged from tiny density fluctuations in the early universe, amplified over billions of years by gravity, creating the pattern we observe today. Webb can trace this structure by mapping the distribution of galaxies across large areas of sky. While individual images show only small patches of the universe, many images can be combined to create larger maps, revealing how galaxies cluster, where the filaments are, where the voids lie. These maps are compared with computer simulations of cosmic structure formation, testing our understanding of how gravity shapes the universe on large scales. The simulations generally match the observations well, supporting our current cosmological model, the Lambda CDM model, which describes the universe as dominated by dark energy and cold dark matter, with ordinary matter making up only a small fraction of the total. Dark matter provides the gravitational framework that holds galaxies together and shapes the cosmic web. Dark energy drives the accelerating expansion of space, pushing distant galaxies apart at ever-increasing rates. Webb doesn't directly observe dark matter or dark energy. These components don't emit light, but their effects are visible in how galaxies move, how the cosmic web is structured, how light bends around massive objects through gravitational lensing. By observing these effects, astronomers can infer the properties of dark matter and dark energy, testing our understanding of these mysterious components that dominate the cosmic inventory. Gravitational lensing, in particular, has become a powerful tool for studying dark matter.
When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of that object bends the light's path, distorting the distant galaxy's image. Sometimes this distortion creates multiple images of the same galaxy, arranged around the lensing object. Sometimes it stretches the background galaxy into arcs or rings. The specific pattern of distortion depends on how mass is distributed in the lensing object. By carefully analyzing these distortions, astronomers can map the distribution of mass in galaxy clusters, including the dark matter that doesn't emit light but contributes most of the cluster's mass. Webb's sharp infrared images reveal lensing effects with unprecedented clarity, allowing detailed mass mapping. These maps show that dark matter is distributed more smoothly than ordinary matter, forming extended halos around galaxies and clusters, providing the gravitational glue that holds structures together. Some of the most spectacular images from Webb show galaxy clusters acting as gravitational lenses, magnifying and distorting background galaxies into beautiful arcs and multiple images. These images are not just aesthetically pleasing, they're scientifically invaluable. The lensing magnification allows Webb to see galaxies that would otherwise be too faint to detect, extending its view even deeper into cosmic time. Some of the most distant galaxies Webb has observed were only visible because gravitational lensing brightened them enough to detect. This technique, using foreground objects as natural telescopes to magnify more distant objects, will be crucial for studying the very earliest galaxies, those forming only a few 100 million years after the Big Bang. These galaxies are intrinsically very faint, too faint for even Webb to detect unaided. But with the help of gravitational lensing, they become observable. Astronomers are systematically studying the most powerful lensing clusters, searching the magnified regions behind them for the faintest, most distant galaxies, pushing toward cosmic dawn. Webb has also contributed to understanding the expansion of the universe itself, specifically the expansion rate, known as the Hubble constant.
This quantity measures how fast space is expanding, how quickly distant galaxies are receding from us. Knowing its value precisely is important for determining the universe's age, its size, its ultimate fate. However, there's currently a problem. Different measurement methods give different values for the Hubble constant. Measurements based on the cosmic microwave background, analyzing the patterns in the early universe's afterglow, give one value. Measurements based on observing distant galaxies and supernovae, using objects whose intrinsic brightness is known to measure cosmic distances, give a different value. The discrepancy is small, about 10%, but statistically significant. It's called the Hubble tension. This tension might indicate that something is wrong with our measurements, some systematic error we haven't identified. Or it might indicate that something is wrong with our cosmological model, some aspect of the universe's behavior we don't yet understand. If the latter, it could point toward new physics, new phenomena, discoveries that would revolutionize our understanding. Webb is contributing to resolving this tension by making more precise measurements of distant objects used to calibrate the cosmic distance scale.
It's observing Cepheid variable stars, stars whose brightness oscillates regularly with periods related to their intrinsic luminosity, making them excellent distance indicators. By measuring these stars more precisely than previous telescopes could, Webb is helping refine our measurements of cosmic distances and therefore the expansion rate. Early results suggest the tension persists. Webb's measurements confirm the values obtained by previous telescopes, not reconciling them with the cosmic microwave background measurements. This is intriguing. It suggests the tension is real, not a measurement error. But what does it mean? Is our cosmological model incomplete? Do we need new physics to explain the discrepancy? Or is there some subtle effect we're overlooking? The answer isn't clear yet. More measurements are needed. More analysis is required. But this is exactly the kind of puzzle that drives science forward, the kind of anomaly that, when finally understood, often leads to breakthroughs.
Let's talk now about something more immediate, more tangible: planets. Webb has revolutionized the study of exoplanets, planets orbiting stars other than the Sun. We've known exoplanets exist since the 1990s, when the first ones were discovered. Since then, thousands have been found, revealing that planets are common, that most stars have planets, that planetary systems are the rule rather than the exception. But discovering planets and understanding them are different challenges. Early exoplanet discoveries revealed mostly that planets existed, providing basic information, like their masses and orbital periods. Understanding their atmospheres, their compositions, their climates, their potential for life, required more sophisticated observations. Webb provides those observations. Its infrared spectrographs can analyze starlight filtered through exoplanet atmospheres during transits, when planets pass in front of their stars from our perspective. During a transit, some of the star's light passes through the planet's atmosphere before reaching us. Molecules in the atmosphere absorb specific wavelengths, creating a spectral signature that reveals which molecules are present. This technique, called transmission spectroscopy, has been used before with other telescopes, but Webb's sensitivity and wavelength coverage make it far more powerful. It can detect molecules previous telescopes couldn't, can absorb fainter planets, can provide more detailed spectra with finer wavelength resolution. The results have been extraordinary. Webb has now characterized the atmospheres of dozens of exoplanets, ranging from hot Jupiters, giant planets orbiting very close to their stars, to smaller planets more similar to Earth in size, if not in other properties. The molecules detected include water vapor, carbon dioxide, carbon monoxide, methane, sulfur dioxide, and more complex organic molecules. Each detection tells a story. The presence of water vapor indicates that water, essential for life as we know it, is common in exoplanet atmospheres. Carbon dioxide and carbon monoxide reveal information about atmospheric chemistry and temperature.
Methane can indicate both geological activity and potentially biological processes, though distinguishing between these sources requires careful analysis. Sulfur dioxide has been detected on some planets, indicating volcanic activity or photochemistry driven by stellar radiation. One of the most detailed atmospheric studies involved WASP-39b, a hot Jupiter about 700 light-years away. Webb's observations detected water, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide in its atmosphere. The sulfur dioxide was particularly interesting because it shouldn't exist in the hot conditions of this planet's atmosphere unless it's being continuously produced by photochemistry, chemical reactions driven by ultraviolet light from the star. This was the first clear detection of photochemistry on an exoplanet, confirming that chemical processes similar to those in Earth's atmosphere occur on other worlds. Another fascinating target is TRAPPIST-1, a small, cool star about 40 light-years away, orbiting by 7 Earth-sized planets. 3 of these planets orbit in the star's habitable zone, where temperatures might allow liquid water to exist. These planets are among the most promising targets for searching for signs of life beyond Earth. Webb has begun observing the TRAPPIST-1 planets, characterizing their atmospheres or determining whether they have atmospheres at all. Some early results were disappointing. Observations of TRAPPIST-1c suggested it might lack a substantial atmosphere, possibly stripped away by intense radiation from its star.
But other planets in the system await observation. The study continues, patiently, systematically, building understanding planet by planet. The mention earlier of K2-18b deserves deeper exploration. This planet is particularly intriguing because it represents a class of worlds we don't have in our solar system, sub-Neptunes, planets larger than Earth but smaller than Neptune. These planets are the most common type of exoplanet we've discovered, yet we don't fully understand their nature. Are they rocky planets with thick atmospheres? Ice worlds with hydrogen envelopes? Ocean planets covered entirely by water? Different possibilities seem plausible, and K2-18b might help us understand which is correct.
Webb detected water vapor and carbon dioxide in K2-18b, along with a possible detection of dimethyl sulfide. On Earth, dimethyl sulfide is primarily produced by phytoplankton in the ocean, making it a potential biosignature, a molecule whose presence might indicate life. However, the detection is not confirmed, requiring additional observations to verify. And even if confirmed, dimethyl sulfide could potentially be produced by non-biological processes we don't yet understand, especially in an environment as alien as K2-18b. The planet orbits a red dwarf star, smaller and cooler than the Sun. Its orbit places it in the habitable zone. But what does habitability mean for such a planet? If K2-18b has a thick hydrogen atmosphere, it might be too hot at its surface for liquid water, despite being at the right distance from its star. The greenhouse effect from all that hydrogen could raise temperatures too high. But models suggest that beneath a hydrogen atmosphere, there might be a layer of high-pressure water, possibly in liquid form, possibly covering the entire planet as a global ocean. Could life exist in such an ocean? We don't know. Life on Earth exists in many environments, from freezing polar ice to boiling hydrothermal vents, from the deep ocean to high atmosphere, from acidic hot springs to extremely salty lakes. Life is adaptable. But all Earth life shares a common origin and fundamental biochemistry. Would life arising independently on another world be similar enough that we could recognize it? Would it produce the same chemical signatures? These are open questions. K2-18b won't answer these questions definitively. Even if dimethyl sulfide is confirmed, even if other potentially biological molecules are detected, we won't be able to say with certainty that life exists there. Extraordinary claims require extraordinary evidence, and atmospheric spectroscopy, while powerful, has limitations. We can detect molecules, but we can't see what's producing them. We can infer conditions, but we can't visit the surface. We can build models, but we can't test them directly. Still, K2-18b represents a step forward. It shows that Webb can detect complex organic molecules in exoplanet atmospheres.
It demonstrates that we have the tools to search for biosignatures, to look for chemical signs that might indicate life. And it reminds us that the search for life beyond Earth is not science fiction. It's science, proceeding carefully, gathering data, building understanding, moving step by step toward answering one of humanity's deepest questions. Are we alone? The answer won't come quickly. It will require observing many planets, detecting many molecules, ruling out non-biological explanations, building confidence gradually. It will require new telescopes, more powerful instruments, decades of work. But the process has begun. Webb is showing us the way. Beyond exoplanets, Webb has revealed new details about our own solar system's formation and history. By observing asteroids, comets, and the outer planets, it's helping us understand the processes that built the solar system 4.5 billion years ago. Asteroids are remnants from the solar system's formation, rocky bodies that never assembled into planets. They preserve information about the early solar nebula, the disk of gas and dust from which the sun and planets formed. Webb has observed several asteroids, analyzing their surface compositions, searching for water ice and organic molecules, materials that might have been delivered to Earth billions of years ago, possibly contributing to the origin of life. Comets are similar remnants,
but formed farther from the Sun, where temperatures were cold enough for ices to condense. They contain water ice, frozen carbon dioxide, frozen methane, and organic compounds, materials from the outer solar nebula. When comets approach the Sun, these ices sublimate, turning directly from solid to gas, creating the characteristic tails that make comets spectacular sights. Webb can analyze these tails, determining what molecules are being released, learning about the pristine materials from the early solar system. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are giant worlds dominated by hydrogen and helium, though they also contain heavier elements in their cores and atmospheres. Webb's observations reveal atmospheric dynamics on these planets, tracking storms, measuring wind speeds, analyzing cloud compositions.
These observations help us understand not just our own solar system's giants, but also the hot Jupiters and other giant exoplanets we observe around other stars. Jupiter's atmosphere, in particular, shows complex weather patterns, with bands of clouds moving at different speeds, massive storms like the Great Red Spot, and auroras near the poles, where charged particles from the Sun interact with Jupiter's magnetic field. Webb's infrared view reveals temperature variations in the atmosphere, showing which regions are warmer and which are cooler, helping meteorologists understand Jupiter's climate. Saturn's rings, made of countless ice particles ranging from dust-sized to house-sized, appear different in infrared than in visible light. Webb's observations reveal temperature variations across the rings, showing how sunlight heats different regions, how the rings cast shadows on Saturn's atmosphere, how the moons embedded in the rings interact with the ring material. Uranus and Neptune, ice giants farther from the Sun, have been less studied than Jupiter and Saturn, but Webb is changing that. Its observations reveal their atmospheres in new detail, showing cloud features, storm systems, and the unusual tilt of Uranus's rotation axis, which is nearly perpendicular to its orbital plane, possibly the result of a massive collision early in the solar system's history. The moons of these planets are equally fascinating. Europa, orbiting Jupiter, has a global ocean beneath its icy crust, making it one of the most promising places to search for life in the solar system. Enceladus, orbiting Saturn, also has a subsurface ocean, confirmed by geysers of water erupting from cracks in its icy surface. Titan, Saturn's largest moon, has a thick atmosphere and liquid methane lakes on its surface, creating a bizarre hydrological cycle similar to Earth's water cycle, but based on methane instead of water. Webb can't image these moons in great detail. They're too small and too far away, but it can analyze light reflected from their surfaces, searching for specific molecules, looking for signs of geological or even biological activity.
These observations complement data from spacecraft that have visited these worlds, like the Cassini mission to Saturn and the upcoming Europa Clipper mission to Jupiter, building a comprehensive understanding of these fascinating places. All of these observations, from distant galaxies to solar system objects, from exoplanet atmospheres to star-forming regions, contribute to a unified picture of cosmic reality. The universe is revealed as a place of endless variety and subtle unity, where the same physical laws operate everywhere, where the same processes of gravity, nuclear fusion, chemistry, and thermodynamics shape everything from the smallest moons to the largest galaxy clusters. And underlying it all is change. The universe is not static, it evolves. Galaxies form and merge, stars are born and die, planets form and migrate. Atmospheres evolve. Life might emerge, thrive, and disappear. Everything is in flux, changing over timescales ranging from seconds to billions of years. Webb allows us to observe this change across cosmic history. We see galaxies evolving over billions of years. We see stars forming and dying. We see planetary systems in various stages of development. We see the universe not as a fixed tableau, but as a dynamic, evolving system, constantly changing, constantly creating new structures, constantly moving towards some future state we can only imagine. This perspective transforms our understanding of our place in the cosmos. We're not separate from the universe, we're part of it. The atoms in our bodies were forged in stellar cores billions of years ago. The planet we inhabit formed from debris left over from the sun's formation.
The conditions that allow life to exist here are the result of billions of years of cosmic evolution, from the Big Bang through star formation, planet formation, and the gradual development of the complex chemistry necessary for life. We exist because of cosmic history. We're products of stellar alchemy, planetary physics, chemical evolution. We're the universe observing itself, matter organized into forms capable of contemplating their own origins, asking questions about existence, seeking understanding.
And tools like Webb extend our senses beyond their natural limits, allowing us to observe phenomena our eyes could never see, to gather information from distances our bodies could never traverse, to witness events from times long before we existed. The telescope is an extension of human curiosity, a physical manifestation of our desire to understand, to explore, to know. Every image Webb returns, every spectrum it records, every discovery it enables, adds to humanity's collective understanding. This knowledge doesn't belong to scientists alone, it belongs to everyone. It's shared freely, published in scientific journals, announced in press releases, displayed in public images and videos. The universe Webb reveals is everyone's universe, a gift of knowledge available to all who care to look. And what a universe it is, vast beyond comprehension, ancient beyond imagination, complex beyond complete understanding, yet governed by laws we can discover, containing phenomena we can observe, telling a story we can gradually piece together through patient observation and careful thought. This is what Webb has revealed. Not secrets kept hidden, but truths waiting to be understood. Not information withheld, but knowledge earned through methodical work. Not mysteries deliberately obscured, but puzzles that yield to persistent investigation. The telescope continues its work, night after night, gathering light, recording data, observing the cosmos. And scientists continue their work, analyzing data, building models, testing hypotheses, gradually converting observations into understanding. And all of us can participate in this process, learning about the discoveries, appreciating the beauty of the universe Webb reveals, marveling at how much we've learned and how much more remains to be discovered. The questions that remain. We've explored what the James Webb Space Telescope is, how it works, and what it has revealed about the universe from its earliest moments to the present day. Now, in this final chapter, let's turn our attention to what remains unknown, to the questions that persist, to the mysteries that even Webb's extraordinary capabilities cannot yet fully resolve. Science is not a destination, it's a journey. Every answer generates new questions.
Every discovery reveals new puzzles. Every solved mystery opens doors to deeper mysteries. This is not frustration. This is the nature of understanding. The more we learn, the more we realize how much we don't know. The expanding circle of knowledge is always surrounded by a larger circle of ignorance. And as our knowledge grows, so too does our awareness of what lies beyond it. Webb embodies this principle perfectly. It has answered many questions, confirmed many hypotheses, extended our understanding in countless ways. But it has also raised new questions, challenged existing theories, revealed phenomena that don't fit neatly into our current models. These unresolved questions are not failures of the telescope or the scientists who use it. They're opportunities for future discovery, invitations to think more deeply, to observe more carefully, to develop better theories. Let's begin with one of the most fundamental questions in cosmology. What is dark matter? We know it exists. We can observe its gravitational effects on galaxies, on galaxy clusters, on the large-scale structure of the universe. We can measure how much of it there is, approximately 5 times more dark matter than ordinary matter in the universe. We can map its distribution through gravitational lensing, seeing how it bends light from distant objects. But we don't know what it is. We don't know what particles comprise it. We don't know how it interacts with ordinary matter beyond gravity. We don't know if it's a single type of particle or a mixture of different particles. We don't know if it's truly fundamental or composed of smaller constituents. We don't even know for certain that it's matter in the conventional sense, rather than some modification of gravity that produces similar effects. Physicists have proposed many candidates for dark matter. WIMPs, weakly interacting massive particles, were long favored, predicted by certain extensions of the standard model of particle physics. Experiments have searched for WIMPs for decades, using detectors deep underground to shield from cosmic rays, looking for the rare interactions that might occur when a dark matter particle collides with an atomic nucleus. So far, no convincing detections.
The parameter space where WIMPs might exist has been largely ruled out, though some possibilities remain. Axions, hypothetical particles much lighter than WIMPs, are another candidate. They were originally proposed to solve a problem in the strong nuclear force, but they could also serve as dark matter if they exist in sufficient quantities. Experiments are searching for axions through different methods, looking for subtle effects that might reveal their presence. Again, no definitive detections yet, but the search continues. Primordial black holes, formed in the early universe rather than from stellar collapse, have been suggested as another possibility. If the early universe contained density fluctuations large enough to collapse directly into black holes, those black holes could still exist today, comprising some or all of the dark matter. Observations constrain how much dark matter could be in this form, ruling out certain mass ranges but leaving others open. More exotic ideas include sterile neutrinos, gravitinos, dark photons, and even more speculative concepts. The truth is, we don't know. Dark matter remains one of physics' greatest mysteries. And while Webb can map dark matter's distribution through gravitational lensing, it cannot tell us what dark matter is made of. That question requires different tools: particle physics experiments, laboratory detectors, theoretical developments that might point toward new physics beyond our current understanding. Similarly mysterious is dark energy, the component driving the accelerating expansion of the universe. While dark matter at least has a clear analogy, it's like ordinary matter but doesn't emit light, dark energy is more conceptually strange. It appears to be a property of space itself, a kind of intrinsic energy density that doesn't dilute as the universe expands. As space grows, more dark energy appears, maintaining constant density while the density of matter decreases due to expansion. This leads to acceleration. In the early universe, when matter was dense, gravity dominated, slowing the expansion. But as the universe expanded and matter thinned out, dark energy became relatively more important.
Eventually, about 5 billion years ago, dark energy's repulsive effect overcame matter's attractive gravity, and the expansion began accelerating. This acceleration continues today and will continue into the future, eventually causing distant galaxies to recede from us faster than light can travel, disappearing from our observable universe. But what is dark energy? The simplest explanation is that it's vacuum energy, the energy associated with empty space itself, sometimes called the cosmological constant. Quantum field theory predicts that vacuum should have energy, though the predicted value is astronomically larger than what we observe, a discrepancy called the vacuum catastrophe, perhaps the worst theoretical prediction in the history of physics. Why is vacuum energy so much smaller than theory suggests? We don't know. Alternative explanations involve quintessence, a hypothetical field that fills space and drives acceleration, but might vary over time or space, unlike the cosmological constant, which is truly constant. Some theories propose modifications to general relativity that might produce acceleration without requiring dark energy at all. Some speculate about extra dimensions of space, about our universe being a bubble in a larger multiverse, about quantum effects on cosmic scales. Again, we don't know. And Webb, while it can measure the expansion history of the universe by observing distant supernovae and galaxies, cannot directly reveal what dark energy is. That understanding will require theoretical breakthroughs, new physics, perhaps experimental discoveries that currently seem unrelated, but might eventually connect to cosmology in unexpected ways. Another profound mystery involves the universe's beginning. The Big Bang theory describes the universe's evolution from a hot, dense state approximately 13.8 billion years ago.
but it doesn't explain what came before, or what caused the Big Bang, or even if before is a meaningful concept. Time itself might have begun with the Big Bang. Space might have emerged at that moment. Asking what came before might be like asking what's north of the North Pole, a question that seems meaningful but actually isn't because it misunderstands the geometry. Yet the question persists.
Did something exist before the Big Bang? Was there a previous universe that collapsed and rebounded? Is our universe part of an eternal cycle of expansions and contractions? Is it one bubble in an endless sea of universes? A multiverse where different regions have different physical laws, different constants of nature, different numbers of dimensions. These ideas are speculative, difficult or impossible to test observationally. Yet they emerge naturally from attempts to extend our theories to the earliest moments. Inflation, a brief period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang, helps explain several features of the universe, including why it's so uniform, why it's geometrically flat, why certain relics predicted by grand unified theories aren't observed. But inflation raises its own questions. What caused it? What field or mechanism drove the exponential expansion? How did it end? Was it a unique event, or does it happen eternally in different regions, constantly creating new universe bubbles? These questions touch the boundaries of science. They venture into territory where observation becomes difficult, where theoretical speculation exceeds our ability to test ideas empirically. Yet they're natural extensions of our knowledge, attempts to understand not just what the universe is, but why it exists, why it has the properties it does, whether things could have been different. Webb cannot answer these questions. No telescope can observe the first instant of the Big Bang. No instrument can see beyond the cosmic microwave background into the opaque plasma that preceded recombination. The earliest moments of the universe might be forever beyond direct observation, knowable only through indirect inference and theoretical extrapolation. Yet even questions we cannot currently answer serve a purpose. They guide research, suggest observations that might constrain possibilities, if not determine answers definitively, inspire theoretical developments that might eventually lead to testable predictions. And sometimes, unexpectedly, answers emerge from directions we didn't anticipate. Consider the question of life beyond Earth.
For most of human history, this was purely philosophical, beyond scientific investigation. We could wonder, we could speculate, but we couldn't observe. The discovery of exoplanets changed this, transforming an ancient philosophical question into a scientific one. Now we can search for biosignatures, we can characterize potentially habitable worlds, we can make the question of extraterrestrial life empirical rather than merely speculative. But we still don't have an answer. We don't know if life exists elsewhere. We don't know if it's common or rare. We don't know if Earth-like planets in habitable zones routinely develop life, or if life requires such specific conditions, such unlikely coincidences, that we might be alone in the observable universe. The question has several parts, each uncertain. First, how common are potentially habitable planets? Webb and other telescopes are helping answer this. Planets appear to be extremely common. Most stars have them. Many are in their star's habitable zone. The ingredients for life as we know it, water, organic molecules, energy sources, seem widespread. This is encouraging for life's prevalence. Second, how likely is life to emerge on a habitable planet? This we don't know. We have only one example, Earth. Life appeared on Earth relatively quickly after the planet's formation, perhaps within a few 100 million years, suggesting it might emerge readily when conditions are right. But perhaps Earth was lucky. Perhaps life requires conditions we haven't identified, coincidences so unlikely that billions of habitable planets might exist, with only a handful developing life. We simply don't know. The origin of life on Earth is still incompletely understood. We know life must have emerged from non-living chemistry, but the specific pathways, the sequence of events, the environmental conditions required all remain areas of active research. Until we understand how life began on Earth, we cannot reliably estimate how likely it is elsewhere. Third, if simple life is common, how often does it evolve into complex, multicellular forms? On Earth, life remained single-celled for billions of years. Complex multicellular organisms only emerged about 600 million years ago.
Was this inevitable given enough time, or does it require special circumstances? We don't know. Fourth, if complex life is common, how often does intelligence emerge? Intelligence seems advantageous, yet it took billions of years to appear on Earth, and it's unclear if it was inevitable or fortunate. Many successful organisms are not particularly intelligent. Intelligence might be rare, a cosmic accident rather than a common outcome. Fifth, if intelligent life is common, how often does it develop technology, civilization, the ability to communicate across interstellar distances? And how long do such civilizations last? Do they destroy themselves? Do they lose interest in expansion and communication? Do they transcend biology in ways that make them unrecognizable or undetectable? Each step involves uncertainties. Multiplying these uncertainties together, we get predictions ranging from millions of technological civilizations in our galaxy to the possibility that we are alone. Both extremes seem remarkable. If civilizations are common, where are they? Why don't we see evidence of their existence? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Proposed solutions to the Fermi paradox range from the optimistic to the sobering. Perhaps civilizations are common but don't communicate, either because interstellar communication is harder than we think or because they choose not to. Perhaps they exist, but we're looking in the wrong ways, searching for radio signals when they use different technologies. Perhaps they're out there, but very far away, so far that their signals haven't reached us yet or are too weak to detect. More sobering possibilities suggest that civilizations don't last long, that they destroy themselves through war, environmental collapse, technological catastrophe, or other means before they can establish lasting presence. Or perhaps intelligence is rarer than we hope, requiring such specific evolutionary paths that Earth might be unusual. Or perhaps we are indeed early, among the first civilizations to emerge in a young universe that will eventually teem with life, but hasn't yet. We don't know.
And while Webb can help by characterizing exoplanet atmospheres, searching for biosignatures, identifying potentially habitable worlds, it cannot definitively answer whether we're alone. That might require detecting an unambiguous signal, an artificial radio transmission, a Dyson sphere around a distant star, megastructures in space, something clearly artificial, clearly the product of intelligence and technology. Or it might require visiting other worlds, sending probes to potentially habitable planets, examining them up close, searching for life directly. Such missions are beyond our current capabilities, but not beyond imagination. Future generations might launch interstellar probes, robotic explorers that travel for centuries or millennia to reach nearby star systems, searching for life, sending data back across the light years. Until then, we search from home, using telescopes like Webb to gather what information we can, gradually constraining the possibilities, slowly building understanding. And we reflect on what it would mean to find life, or to discover we're alone. Both answers would be profound. Both would change our perspective on existence, on our place in the cosmos, on the meaning and responsibility of being alive. Another question that persists involves the ultimate fate of the universe. We know the universe is expanding. We know the expansion is accelerating. Current models suggest this acceleration will continue indefinitely. What does this mean for the future? In the short term, cosmically speaking, not much changes. Galaxies will continue to exist, stars will continue to shine, planets will continue to orbit. But over hundreds of billions of years, the effects of accelerating expansion become significant. Distant galaxies will recede beyond our cosmic horizon, disappearing from view as space carries them away faster than light can traverse the growing distance.
Eventually, only our local group of gravitationally bound galaxies will remain visible. The rest of the universe will have receded beyond observation. Star formation will gradually cease as galaxies exhaust their gas supplies. Existing stars will age and die.
Red dwarfs, the smallest and longest-lived stars, will burn for trillions of years, but even they will eventually exhaust their fuel. The universe will grow dark. Dead stars, white dwarfs, neutron stars, and black holes will dominate. Planets will be ejected from star systems through gravitational interactions or will spiral into dead stars. Matter will slowly decay. Protons might eventually break down if certain grand unified theories are correct, though this remains speculative. Black holes will slowly evaporate through Hawking radiation, a quantum process that causes them to lose mass over unimaginably long timescales. Eventually, perhaps after a Google years, 10 to the power of 100 years, the universe might consist of nothing but dispersed elementary particles, photons stretched to enormous wavelengths, and perhaps some exotic remnants we haven't predicted. It will be cold, dark, empty, a far cry from the vibrant universe we observe today. This is the heat death, the gradual running down of the universe as entropy increases, as energy spreads out, as differences in temperature and density smooth away. It's a quiet ending, not a catastrophic collapse, but a gentle fading, the universe growing ever more uniform, ever more still, ever colder and darker. But this prediction assumes our current understanding is correct. It assumes dark energy remains constant, that it doesn't change over time. If dark energy increases, the expansion could accelerate faster, eventually tearing apart galaxies, stars, planets, even atoms in a big rip. If dark energy decreases or reverses, expansion could slow, stop, and reverse, leading to a big crunch, the universe collapsing back to a dense state, perhaps to bounce and begin anew. We don't know which scenario is correct because we don't know what dark energy is or how it behaves over cosmic time. We observe its effects now, but we cannot predict its future evolution with certainty. The universe's ultimate fate remains an open question. These cosmic-scale questions can feel abstract, distant from daily life, but they connect to more immediate mysteries, questions about the nature of reality, the laws that govern existence, the fundamental structure of space and time.
Quantum mechanics, our best theory of the very small, describes reality in ways that seem strange, even paradoxical. Particles exist in superpositions of states until observed. Entangled particles affect each other instantaneously across arbitrary distances. The act of measurement seems to play a fundamental role in determining reality. These features have been confirmed experimentally countless times, yet their interpretation remains debated. What does quantum mechanics mean? Is the wave function, the mathematical description of a quantum system, a real thing or just a tool for calculation? When a measurement occurs and superposition collapses to a definite outcome, is this a physical process or just an update of our knowledge? Do unobserved quantum possibilities somehow exist in parallel universes, as the many worlds interpretation suggests, or is there only one reality with genuine randomness at the quantum level? These questions touch the foundations of physics. They are not merely philosophical, but have implications for understanding the universe at the deepest level, and they remain unresolved despite nearly a century of quantum mechanics. We can calculate with extraordinary precision, predicting experimental outcomes with stunning accuracy, yet we disagree on what the theory means, what it tells us about reality. Similarly mysterious is the reconciliation of quantum mechanics with general relativity, our theory of gravity and space-time. Both theories are extraordinarily successful within their domains. Quantum mechanics describes atoms, particles, and forces with incredible accuracy. General relativity describes gravity, from falling apples to black holes and the expanding universe, with equal precision. But they seem fundamentally incompatible. General relativity treats space-time as smooth and continuous. Quantum mechanics suggests everything is discrete, quantized, fundamentally uncertain.
Attempts to merge them into a theory of quantum gravity have proven extraordinarily difficult. String theory, loop quantum gravity, and other approaches have been developed, but none have been confirmed experimentally, and none have achieved the status of accepted theory.
This might seem like an academic problem, relevant only in extreme conditions like the center of black holes or the first instant of the Big Bang, but it represents a fundamental gap in our understanding. We don't have a complete theory of physics. We have two partial theories that work brilliantly in different regimes, but cannot be fully unified. Somewhere in the reconciliation of quantum mechanics and general relativity might lie insights that transform our understanding of space, time, matter, and causality. Webb cannot directly address these questions. They require theoretical developments, perhaps experimental discoveries in particle physics, perhaps observations of phenomena we haven't yet imagined. But they remind us that even our most successful theories are incomplete, that mysteries remain even in the foundations of physics, that understanding is always provisional, always subject to revision as new evidence and new ideas emerge. Let's return to more concrete mysteries, puzzles that observations might help resolve. One involves fast radio bursts, brief, intense pulses of radio waves coming from distant galaxies. These bursts last only milliseconds, but release enormous energy, as much as the sun emits in days or weeks, all concentrated into a fraction of a second. The first fast radio burst was discovered in 2007 in archival data. Since then, hundreds have been detected. Some sources emit single bursts and are never heard from again. Others emit repeated bursts from the same location. The physical mechanism producing them remains uncertain. Leading theories involve neutron stars, extremely dense remnants of massive stars, perhaps with extraordinarily strong magnetic fields, perhaps merging with other objects, perhaps experiencing starquakes or magnetic reconnection events that release enormous energy. But we're not certain. Fast radio bursts might represent a phenomenon we haven't anticipated, physics we don't yet understand. They come from too far away to study in detail. We can locate the host galaxies, but cannot see the objects producing the bursts directly.
We can measure properties of the bursts themselves, their duration, their frequency, their polarization, but converting these measurements into understanding of the source requires theoretical models that might be incomplete. This is common in astronomy. We observe phenomena from vast distances with limited information. We build models to explain them, but multiple models might fit the same data. Distinguishing between possibilities requires additional observations, different measurements, sometimes lucky breaks when we observe something unexpected that rules out some hypotheses and supports others. Fast radio bursts are just one example. The universe contains many phenomena we don't fully understand. Gamma-ray bursts, extremely energetic explosions seen across the universe, were mysterious for decades before we understood they come from supernova explosions of certain massive stars or from colliding neutron stars. Ultraluminous X-ray sources, objects that emit more X-rays than should be possible from stellar mass black holes, might be intermediate mass black holes or might represent extreme accretion onto smaller objects. The exact mechanism remains debated. These mysteries are not kept secret. They're published in scientific journals, discussed at conferences, featured in research proposals requesting telescope time. They're open questions, known to be unresolved, waiting for the observations or theoretical insights that will finally explain them. And sometimes mysteries resolved in unexpected ways. Pulsars, rapidly pulsating radio sources, were discovered in 1967. Initial observations were so regular, so precise, that they were briefly wondered to be artificial signals from extraterrestrial intelligence, nicknamed LGM for Little Green Men. Further observations revealed them to be natural, rotating neutron stars with powerful magnetic fields, beaming radiation like cosmic lighthouses. Each time the beam sweeps past Earth, we detect a pulse. Mystery solved, though the solution revealed a new class of exotic objects we hadn't imagined. Quasars followed a similar path. Discovered in the 1960s, these bright point-like objects emitted enormous energy, but seemed to be stars based on their appearance.
Spectroscopy revealed they were actually extremely distant, meaning they must be intrinsically very luminous to appear so bright from so far away. Nothing known could produce such energy. The mystery persisted until the 1980s, when it was realized that quasars are powered by supermassive black holes at the centers of galaxies, consuming matter at prodigious rates, converting gravitational energy to radiation with efficiency far exceeding nuclear fusion. Mystery solved, and again the solution revealed phenomena, supermassive black holes and their feeding processes that transformed our understanding. Webb is now observing quasars in unprecedented detail, seeing how they affect their host galaxies, how they grow over cosmic time, how they relate to galaxy evolution. Every mystery solved opens new questions. How do supermassive black holes form? How do they grow so large? How do they affect star formation in galaxies? Do all galaxies harbor central black holes? The questions continue, deeper and more sophisticated than before, but still questions, still invitations to further investigation. This pattern repeats throughout the history of science. Mystery leads to observation. Observation leads to hypothesis. Hypothesis leads to testing. Testing leads to understanding. Understanding reveals new mysteries. The cycle continues, each revolution expanding knowledge, each answer generating new questions. Some mysteries might never be fully resolved. The nature of consciousness, the subjective experience of existence, seems to resist purely physical explanation, despite being clearly associated with physical processes in the brain. Perhaps consciousness will eventually be explained in terms of information processing, neural dynamics, and quantum effects. Or perhaps it represents something fundamentally beyond physical description, though what that might mean is unclear. The question of why the universe exists at all, why there is something rather than nothing, might be unanswerable. Perhaps existence requires no explanation. Perhaps it's a brute fact, a starting point beyond which no further questions make sense. Or perhaps there is an explanation in terms of quantum fluctuations, multiverse generation, mathematical necessity, or concepts we haven't yet formulated.
We might never know. These limits of knowledge are not failures. They're reminders of our place in the universe, finite beings with finite capacities attempting to understand infinity. The remarkable thing is not that some questions remain beyond us, but that so many questions yield to investigation, that the universe is comprehensible at all, that the laws governing reality are discoverable through observation and thought. And the process of discovery is itself valuable, independent of whether all mysteries are eventually solved. The journey of exploration, the gradual accumulation of understanding, the satisfaction of solving puzzles, the beauty of the cosmos revealed through observation, all of this enriches human existence. We are curious creatures. We seek to understand. This seeking is part of what makes us human. Webb embodies this seeking. Every observation it makes, every image it captures, every spectrum it records, represents humanity reaching beyond immediate survival needs to pursue understanding for its own sake. We build telescopes not because they feed us or shelter us, but because we want to know, because we cannot help but wonder, because the universe calls to us, and we respond by looking, by questioning, by seeking answers. What has Webb kept hidden? Nothing, truly. Everything it observes eventually becomes public. All its data enters archives accessible to researchers worldwide. All discoveries, once understood, are shared through publications and announcements. The delay between observation and announcement is not secrecy, but science working properly, ensuring that what is announced is correct, that interpretations are justified, that understanding is solid. The real secrets are not hidden data, but unanswered questions, mysteries that persist despite observation, phenomena we've seen but don't yet understand. These are not kept from the public. They're known puzzles, open problems, subjects of ongoing research. Scientists are as curious about them as anyone, perhaps more so, driven by professional dedication to understand, to explain, to solve the cosmic riddles. And some questions might never be answered conclusively.
Some mysteries might remain perpetually just beyond our grasp, retreating as we advance, always suggesting more than they reveal. This is not frustration. This is the nature of a universe that is deeper and richer than any finite understanding can fully capture.
But within these limits, we can accomplish extraordinary things. We can observe the universe across billions of light years. We can see light that has traveled for most of cosmic history. We can analyze the composition of worlds we will never visit. We can trace the evolution of galaxies over billions of years. We can search for signs of life beyond Earth. We can contemplate the ultimate fate of reality itself. These capabilities would seem like magic to people from earlier eras. Our ancestors looked at the same night sky, but saw it without understanding, without knowledge of what stars are, how distant they are, how the universe is structured. In just a few centuries, we've gone from speculation to observation-based understanding, from wondering about the heavens to analyzing them in detail. And the progress continues. Webb is not the final telescope. Already plans are being made for future instruments, telescopes even larger, more sensitive, capable of observing phenomena currently beyond our reach. Ground-based telescopes with mirrors 30 meters across are being built, instruments that will see farther and clearer than anything before. Space telescopes with different capabilities, different wavelengths, different techniques are being designed. The search for extraterrestrial intelligence continues, with new radio telescopes, new search strategies, new ideas about where to look and what to look for. Proposals for interstellar probes are being refined, missions that might launch in coming decades to visit nearby star systems, to search for planets, to look for life up close. The questions persist, but so does our determination to answer them. So does our curiosity. So does our capacity for wonder at the magnificent cosmos we inhabit. Webb shows us the universe as it is, beautiful and mysterious, vast and ancient, comprehensible and yet full of puzzles.
It reveals galaxies in the cosmic dawn, stars being born, planets with complex atmospheres, structures light years across, shaped by forces we can calculate. It shows us both what we understand and what we don't, both our knowledge and the limits of that knowledge. And perhaps that's the most valuable thing any telescope can do. Not just to confirm what we think we know, but to surprise us, to challenge us, to show us phenomena that don't fit our models, that force us to think harder, to observe more carefully, to develop better theories. The universe doesn't care about our theories. It simply is what it is. Our job is to observe it accurately, to describe it honestly, to acknowledge when we don't understand, to keep searching for better explanations. Science is not about being right. It's about being less wrong over time, gradually correcting errors, refining models, approaching truth asymptotically, even if we never fully arrive. Webb is a tool in that process, a magnificent tool, an engineering triumph, a testament to human ingenuity and cooperation, but still just a tool, valuable only because of what we do with the information it provides. The telescope gathers light. We give that light meaning. And the meaning we extract is not just abstract knowledge, it's perspective. It's understanding our place in space and time. It's recognizing that we're part of something vastly larger than ourselves, that we exist on a planet orbiting an ordinary star in an ordinary galaxy among billions of galaxies, that we're made of material forged in stellar cores, that we're momentary patterns of organization in a universe trending towards disorder, that our existence is both insignificant on cosmic scales and profoundly remarkable in its improbability. This perspective can be humbling. We are small. Our planet is small. Our sun is one among hundreds of billions. Our galaxy is one among hundreds of billions. We exist for cosmically brief moments. We will die and be forgotten. Our civilizations will crumble. Our planet will eventually be consumed by the sun. Our galaxy will merge with others and lose its identity.
Eventually, the universe itself will grow cold and dark and empty. But perspective can also be elevating. We are the universe become aware of itself.
We are matter organized into forms capable of contemplation, of appreciation, of wonder. We can observe the cosmos and understand what we're seeing. We can trace our origins back through billions of years of cosmic evolution. We can contemplate the future, imagining what might be. We can create beauty, meaning, knowledge, love, despite living in a universe that seems fundamentally indifferent to our existence. This is extraordinary. This is worth celebrating, not despite the universe's vastness and our smallness, but because of it. Because we can comprehend the vastness, because we can find meaning in the smallness, because we can look at 13 billion light years and understand what we're seeing. Webb enables this. Every image it returns, every discovery it makes, adds to the sum of human knowledge, enriches our collective understanding, provides material for wonder and contemplation. The telescope looks outward into space and time, but its findings ultimately turn us inward, toward questions of meaning and purpose and significance. What does it mean to exist in such a universe? What should we do with our brief time? How should we relate to each other, knowing we're all made of stardust, all products of the same cosmic evolution? How should we treat our planet, knowing it's the only one we have, perhaps the only one in light years harboring life? These are not scientific questions. They're philosophical, ethical, existential questions. But science informs them. The knowledge Webb provides about the universe, about our origins, about the rarity or commonness of planets like Earth, all of this contextualizes human existence in ways that matter for how we understand ourselves and our responsibilities. And the process of discovery itself models something valuable: patience, honesty, humility, cooperation. Science works because scientists are willing to be wrong, to change their minds when evidence demands it, to build on each other's work, to share findings openly. These virtues, exemplified in the scientific process, have value beyond science. Webb required international cooperation, thousands of people working together across decades to design, build, launch, and operate an instrument of unprecedented complexity.
This cooperation succeeded despite political tensions, economic pressures, technical challenges. It shows what humans can accomplish when we work together toward shared goals. And the knowledge Webb generates belongs to everyone. The images are public. The data is archived and accessible. The discoveries are published in journals anyone can read. This openness, this sharing of knowledge, represents humanity at its best, creating understanding not for individual gain, but for collective benefit. So what has Webb really shown us? Not hidden secrets, but open mysteries. Not conspiracies, but complex questions requiring patient investigation. Not final answers, but invitations to keep exploring, keep questioning, keep seeking understanding. The universe revealed by Webb is one of endless fascination, where every answer leads to new questions, where beauty and mystery coexist, where the familiar and the strange intertwine. It's a universe that rewards curiosity, that offers infinite opportunities for discovery, that remains fundamentally inexhaustible despite our best efforts to comprehend it. And this is perhaps the most profound revelation of all. Not any specific discovery about galaxies or exoplanets or dark matter, but the realization that the universe is knowable yet endless, that we can understand it without exhausting it, that every horizon we reach reveals new horizons beyond. This should inspire not frustration but excitement. We will never run out of questions. We will never finish exploring. Future generations will make discoveries we cannot imagine, will develop technologies we cannot conceive, will understand aspects of reality we haven't begun to contemplate. The adventure continues, perpetually, endlessly, inviting each new generation to contribute their part to the great human project of understanding existence. Webb is one chapter in this ongoing story,
A remarkable chapter, certainly, revealing the universe in unprecedented detail, challenging our understanding, expanding our knowledge. But still just one chapter. The story continues. The universe awaits. The questions persist. And we, temporary patterns of organized matter on a small planet orbiting an ordinary star, continue to look up, to wonder, to seek understanding.
Not because we must, but because we can. Not because it profits us, but because it enriches us. Not because it's easy, but because it's worthy of the effort. I find myself thinking about all of this, about what we've learned and what remains unknown, and I'm struck by something that seems both obvious and profound. We live in an age of extraordinary knowledge. We can observe light from billions of years ago. We can analyze the atmospheres of distant planets. We can map the structure of the entire observable universe. Our ancestors could barely imagine such capabilities, yet here we are, doing routinely what would have seemed miraculous just generations ago. And yet, perhaps the most important thing Webb has taught us is not what it has shown us, but what it has reminded us about. It has reminded us that mystery is not the absence of knowledge, but the presence of questions worth asking. That understanding is not a destination we reach, but a journey we undertake. That the universe is not a puzzle to be solved and set aside, but an endless source of wonder that rewards every effort to comprehend it. When I think about what Webb has kept hidden, I realize the question itself misunderstands how discovery works. Nothing is being kept from us. We are keeping ourselves from understanding by not yet having asked the right questions, by not yet having made the right observations, by not yet having developed the right theories. The universe is an open book, but it's written in a language we're still learning to read. What moves me most is not the answers we've found, but the questions that remain. Each mystery represents an invitation, an opportunity, a direction for future exploration. The unanswered questions are not failures of science, but signs of its vitality, evidence that we haven't exhausted reality, that there's always more to learn, always deeper to go. And this seems to me profoundly optimistic. We are not at the end of discovery, but somewhere in the middle of an endless journey. Future generations will look at our current understanding the way we look at the knowledge of past centuries, appreciative of how far we'd come, but aware of how much further there was to go. They will have capabilities we cannot imagine. They will answer questions we haven't formulated. They will explore regions of reality we haven't conceived. But they will do so building on what we've learned, using tools we've developed, following paths we've begun to trace. Webb is part of that legacy, part of the ongoing human endeavor to understand, to explore, to know. And every person who looks at Webb's images, who learns about its discoveries, who feels wonder at the universe it reveals, becomes part of that endeavor too. So here is my question for you as you finish this journey through what Webb has shown us. What will you do with this knowledge? How will it change how you see the night sky, knowing that every point of light is a sun, perhaps with planets, perhaps with life? How will it affect your sense of your place in existence, knowing you're made of material created in stellar cores billions of years ago? How will it shape your priorities, understanding that you exist on a rare planet in a vast cosmos, for a brief moment in cosmic time? The universe has shown us wonders beyond imagination. What will we do with the wonder?